Hi, my name is Ekta, and Ahmet and I will be discussing hardware acceleration opportunities for homomorphic encryption in the context of our recent work, Medha, Microcoded Hardware Accelerator for Computing Unencrypted Data. So, in this presentation, I'll discuss the motivation and background, mainly the challenges that we face for accelerating homomorphic encryption schemes, and I'll give a brief description of the RNS Hyun scheme that we used for our implementation. And then Ahmed will walk you through our work, Medha, and also discuss the future scope. So, as a motivation, we all know that homomorphic encryption allows computation, privacy-preserving computation on the cloud. So a user can send his encrypted data to the cloud and get back the encrypted result. And the cloud at no point of time will know what the data or the results was. And this is a very nice application for privacy preserving computations, data storage, etc. And although these schemes have been existing for now more than a decade, their implementations are still not in commercial use. And one of the main challenge for this is that these schemes are computationally intensive. For example, if I have to do an integer multiplication between two integers, if I do it plain text and compare it to homomorphic evaluation, this will be 100,000 times more expensive. And this is a huge, huge gap compared to plain text computation that we are trying to bridge. And this challenge is also contributed by the huge parameter sets. So recently, NIST finalized some post-quantum cryptographic schemes, and these schemes had polynomials of degree 200,000 or something, and coefficients of size 23 or 30 bit. Compared to these, if we want to have secure homomorphic encryption schemes, then we have to choose this huge parameters. And even at these parameters, we can only do the very basic, for example, logistic regression or linear regression. So if you have to do linear regression, which involves one multiplication and accumulation, then you can choose coefficients of size 100 bit or a polynomial of size 4096, which will provide you, let's say, a depth of 2. If you have to go a little bit above and have to do some function approximation, which requires a multiplicative depth of 4 or 5, you already have to double your polynomial size, polynomial degree, and the coefficient size. For going to logistic regression from linear regression, you already need to go 4 times more expensive polynomial degrees and coefficient size. And this is just the basic machine learning applications. If you have to go for neural network evaluations, most of these will require bootstrapping, and you have to choose much higher parameter sets. So this is how expensive homomorphic encryption schemes are compared to the state-of-the-art post-quantum schemes, for example. And because of this huge parameter size, the number of coefficients in a polynomial and the size of these coefficients, we face a lot of polynomial arithmetic expensive operations because we have to deal with large degree polynomials. We have to multiply them, we have to add them, and multiplication has an order of n square complexity. And long integer arithmetic, because the bit size of these coefficients is huge. Another major problem that we face because of these huge parameters is the memory management, because if we have to store, let's say, two integers for multiplication, we just need, let's say, 232-bit storages. But if we have to store a homomorphic ciphertext, which encodes these two integers and then multiplies them, we'll require megabytes of storage. And this is a huge amount of storage. And the problem is that when we try to implement these, we try to do it on FPGA so that we can prototype our implementation, we can verify implementation in real time. And FPGA's on-chip memory is limited. So we are hardly able to store one whole ciphertext in one FPGA and then process it with all the keys that are required. Now, if we try to use the data on off-chip, which is more than what is available on-chip, then we have to face the communication backlog because off-chip to on-chip data transfer is very slow. These are the challenges that we face. For the first challenge, the computational intensity, we go for hardware acceleration because making a dedicated hardware for these homomorphic encryption schemes is a hope towards bridging the gap compared to the plain text computations. And for the long integer arithmetic, this problem is solved using RNS. And how RNS or residue number system works is, the idea is when you have big coefficient modulus, for example, this capital Q here, we want to split it into smaller moduli, QIs, which when multiplied can give me the same size, a capital Q. And this allows me to process these separate residues independently. For example, I have this big arithmetic polynomial that I have to perform mod Q. I can try to split it into different QIs here and perform them separately. So this will allow me to go for some parallelism instead of having to do in one go. And when I want to combine the result back, when I want to get the original result, I can apply Chinese remainder theorem CRT, and I'll get the result mod Q. So with this, I get small coefficients that I have to deal with because these QIs are much, much smaller compared to one big capital Q. And I am also available to provide parallel computation. So I can make different threads for each of them, which I'll show in the next example. So if, for example, I have a big ciphertext, which is like this thick rope, it is secure, but it is really hard to implement in hardware. So what I'll try to do is, I'll try to break this rope into smaller strings, which are my moduli Q0 to QL minus 1. And now, if I have to perform computations, how this looks like is, I have these two ciphertexts, C0 and C0 prime, which I want to add, subtract, or multiply. Then to break them down into threads, I will just perform mod Q0, mod Q1, up to L minus 1 if I want to break them in L threads. And I have now L components of these original ciphertexts, and I can perform small additions, subtractions, or multiplications on these smaller portions. So I do not need one big multiplier. I can just do with small multiplications. And this also gives me the opportunity to do these operations in parallel. And how this works or looks like for different homomorphic operations is, if I take addition, for example, and I have my ciphertext C and C prime that I want to add, and these ciphertexts have two components. And these components are, let's say, stored in a separate memory that is available with these threads here. So I have the Q0 component of these two ciphertexts stored in the Q0 thread, and so on. Now when I want to add them, I just add it component-wise, so I never need to perform a data transfer across the threads for addition. So whatever is within the thread stays within the thread. I get the result within the thread. Similarly, when I go for multiplication, here I have to do 4 multiplications, but this is still within the components that are stored in the thread. So I do not have to perform a data transfer across threads. These can work perfectly in parallel. But now the problem comes because we have 3 components in our multiplied result, dmult, and this is non-linear because my ciphertext always had 2 components, and now I have a 3rd component. And if I do not reduce it back to 2, this will go exponentially, and this will cause a lot of problem to manage so many ciphertexts. So we need to go for something called linearization. And the goal of linearization is that we have 3 ciphertexts, 3 components in the ciphertext after multiplication, and we want to reduce it back to 2. And how this works is, I started with L separate threads, but after multiplications, these threads have some errors, huge error growth, and they are quite weak to perform this kind of a step. So we add an extra thread to it, the QL thread, and then we multiply the value D2 component stored across 3 L threads with the key switching keys that are pre-generated, and we accumulate them. This means that for each of these Q0 up to QL moduli, I need to multiply the components here with the key switching keys, add them, and reduce them mod Q0. And after we have done this for all the threads, we'll just perform a mod down, drop this extra thread here, and we'll have our 2 components in the ciphertext. But this communication here is very expensive because all the threads from the previous layer here need to then communicate with every thread in this layer. And this, for example, for mod Q0, all the results will be accumulated here. Same will be done for mod Q1 as well. And this means that if I have threads spread across my hardware, then they all need to communicate with every other thread. And this is an order of n square complexity, and these are very difficult to place in hardware This is another major hardware design challenge that we face when we try to do hardware implementation for homomorphic encryption schemes. And now Ahmet will discuss our work, how we managed these challenges, and how we overcame the problems.
Like, could you stop, please, sharing? So. Okay. Can you see my screen?
Yes.
Okay,
yeah.
Great. So after Aikata's introduction now, I will present our papers, Medha, Microcoded Hardware Accelerator for Computing on the Encrypted Data. This is a joint work with our crypto engineering group at Graz University of Technology and Samsung Advanced Institute of Technology. So before I go into detail, first I would like to give a summary of our contributions. So at the end, what we propose is a design and implementation of a programmable and a flexible hardware accelerator for a RNS variant of the CKKS scheme. And to be able to achieve that, we propose and implement the polynomial arithmetic unit with the instruction level parallelism. And to reduce to implementation complexity, we propose and implement several optimizations on the on-chip memory design and the placement on the FPGA platform. On the top of that, to be able to provide the parameter flexibility, we propose a flexibility method for the polynomial degree, and also we implemented it in our design. And finally, we verified and benchmarked the micro operations and the application level operations on a real Xilinx Alveo U250 board. And if you at the end, when we compare our work with the Microsoft Seal library running at 2.3 gigahertz, our accelerator showing 78 times improvement compared to the Seal. Okay, before I explain our design, let's look at the overview of the hardware accelerator works in the literature. When we look at the work, we see two main tracks. The first one is the real hardware accelerators actually prototypes in the FPGA and ASIC platforms. And the second track is a simulation-based modeling, the works kind of hardware accelerators for the HE schemes. And there are some examples. When we look at these real hardware prototypes, we see mostly the FPGA-based works, HAWS and AHX, and we see one ASIC work, CoFHE. And on the other hand, for the simulation-based works, we see several recent works like F1, BTS, and Crater Lake. Although they present really impressive results, their results mostly depends on RTL level or C modeling level simulations. And now I will start the focusing on our actual architecture. So before we start the implementation, we set several design goals for ourselves. The first one and the most important was that we wanted to implement a design such that we will be able to implement and verify it on a real FPGA. And as an FPGA platform, we select Xilinx Alveo U250 card. And since homomorphic encryption is already memory bound, we wanted to eliminate off-chip memory communication during the homomorphic computations. And lastly, to be able to support applications, we wanted to support at least polynomial degree 2 to the power 14 with the individual RNS modular sizes 54 to 60-bit for RNS variant of CKKS. And we start with the design of a flexible instruction set architecture for each RNS space. So in our design, for each RNS space, we design one residue polynomial arithmetic unit, which can perform a polynomial addition, subtraction, polynomial multiplication, NTT, inverse NTT operations, and automorphism operations. And all of these operations are required to perform the main building blocks of the RNS-based CKKS scheme. And now Aikata mentioned about the threading and with the RNS system, threading and the dividing operation into smaller chunks and performing them in parallel. Now, all of each thread now in our implementation is represented one RPOW unit. And this is the overall of architecture of one RPOW. And we have two main cores. The one is NTT core with 16 butterfly units. And we have one smaller dyadic core with the 4 dyadic units. And on the top of that, we have memory blocks to store the input residue polynomials, intermediate values, also the evaluation keys required during the homomorphic multiplication and the rotation operations. So why do we select two separate cores? If you look at the inner loop of the key switching operation, it actually executes one entity and several coefficient-wise multiplication operation. So our goal was that this is the part of the key switching, and this is the one of the most time-consuming and the complex part of the homomorphic encryption routine. That's why we wanted to parallelize this part to improve the performance and reduce the complexity. Now, if we look at this operation, we see that after the homomorphic multiplication, we have 3 components, D0, D1, and D2. And during the key switching part, what we do is we take the RNS basis of D2 component, and first we apply the inverse NT to the first RNS base, then we do the modular reduction, and then we apply NTT for different remaining bases. And then finally, we multiply the results with the corresponding key switching keys. And we repeat this operation for all RNS bases of the D2 component of the multiplied ciphertext. Finally, all results needs to be summed up to have the final result of the key switching routine. As you can see, during the key switching, we have to perform several inverse NTT, NTT, and coefficient-wise multiplication operation. So here we present this how we schedule these operations. So we parallelize this multiplication and NTT. So we start with the as I said before, we have 2 different cores. One is a NTT core, and one is a dyadic core who can perform just dyadic multiplication, addition, and subtraction operations. So the first we start with the NTT. And when we perform the first entity, of course, in parallel, we cannot do a dyadic because the next dyadic operation depends on the result of the previous entity operation. After we finish the first entity operation using the main cores, then what we do is we start the dyadic multiplication using the key switching keys and the results of the previous entity operation. And then next, at the same time, instead of idling the main entity unit, entity starts performing the entity operation for the second RNS space. In that way, we were able to process the key switching multiplication and entity operation in parallel. This increases the utilization of the arithmetic unit in our design. And here the next step, again, we perform the direct multiplication for base 1 and entity operation for the base 2. And then we continue it like this until the very end. We just finish our operation with the direct multiplication. So this parallel execution of entity and direct cores for the key switching procedure result in a 40% reduction in cycles. And we achieve this with a cost, of course, and we use a 16 butterfly entity and the 4-core direct units. And we analyze this operation to select the number of cores, because as you can see, direct core using 4 times less resources than the entity core. And the main reason is that when we look at the latency of one entity with the 16 core, we see that the latency roughly is n divided by 32 times log n. And when we look at the latency of 2 direct multiplications with the 4-core direct unit, it is 2 times n over 4. And as I said before, we target at least n is equal to 2 to the power 14. And when we substitute this n with the 2 to the power 14, the latency of one entity is roughly 7,200 clock cycle. And latency of 2 direct operations is roughly 8,200 cycle. So the goal was that we can keep the latency of these 2 operations very close to each other. And then basically when we perform them in parallel, we will not waste any cycle, and we can utilize our hardware. We can increase our hardware utilization during the homomorphic computations. So now I will give again a short summary. So in the architecture part, we have our main architecture, and for each RNS base, we implemented one RNS unit, one RPA unit, which can perform parallel entity and direct multiplication operations. Now we will mention the optimizations we do on the on-chip memory design for each RPA unit. So when we design our on-chip memory, our goal was that during the homomorphic operations, eliminating the off-chip memory completely and using only on-chip memory resources. So to be able to do that, first, we have to analyze the peak memory requirement of one RPA during the homomorphic multiplications. And what are the source of the memory burden for one RPA was that first, the residue polynomials of the input ciphertext and the output ciphertext. Also, during especially key switching operation, we have to create and store several intermediate residue polynomials. Also, homomorphic multiplication and the homomorphic rotation operations require evaluation keys. So we have to also store them in our on-chip memory to eliminate off-chip memory communication. And finally, for the entity and inverse entity operations, we have to store some constant, what we call TVDL factors. If you want to give an example for our for a polynomial degree to the power 14 with using only 10 RNS base of 54 and 60 bits, then our calculations show that each RPA needs to store at least 49 polynomials of size 2 to the power 14 for residue polynomials and the keys. This calculation even excludes the memory need for the constants of entity and inverse entity. Of course, when we look at our platform, on-chip DRAMs and URAMs alone cannot fulfill this requirement if you want to have a reasonable clock frequency. That's why we worked on several techniques to optimize and reduce the on-chip memory requirements. The first thing is we worked on the on-the-fly evaluation key generation. And the second, we try to utilize the leftover bits in the BRAM and URAM used in our power designs. And finally, again, we worked on the on-the-fly TVDL factor generation for entity and inverse entity. Now we will start with the key generation. So if you look at the key switching keys used during the preliminarization operation of the RNS-based CKKS, we see that the first key is basically generated from a uniformly random distribution. And the second key, we call the key 0 and key 1. Key 1 is a function of key 0 and the secret key. So in a straightforward implementation, what we will do, key 0 will be generated. Then using the secret key and the key 0, key 1 will be generated again offline when we generate our parameters. And then these pre-generated polynomials will be sent to the FPGA, and they will be stored in the on-chip or off-chip memory. And they will be then used during the homomorphic computations. However, this will increase the memory requirement of the operations a lot. So our solution was that since the first key is generated uniformly as a uniformly random from a uniformly random distribution, so we use several seeds, and one PRNG function to generate this the first key, and then again the second key is generated using the function of first key and the secret function. So here's the updated key generation procedure. So now we have our seeds, and now seeds are sent to the PRNG, and using this function, the first key is generated. And then using the secret key and the first key, we generate the second key. Now, instead of sending both keys to the FPGA, what we did, we send the second key to the FPGA and store it because it depends on the secret key. But instead of sending and storing the first key to the FPGA, we just send the seeds and we implement the PRNG function on the FPGA. That way, we can now read our seeds in the FPGA and send them to the PRNG, and we can generate the corresponding the key 0 in the FPGA on the fly instead of storing it. So this basically reduced the memory requirement of the evaluation key storage by 50% at the expense of very small seed memory, and again very small PRNG functions, which we implement using Trivium Cipher. And the second optimization we used was utilizing the leftover bits and the BRAM and URAMs. So when we look at the Xilinx FPGA structures on the Alvea board, we see that one URAM address can store 72 bits. And when we look at the BRAMs, we can configure in different ways. We can store to each address either 18 bits or 36 bit or 72 bits. So when we look at these numbers, if you want the full utilization of one BRAM or URAM address, what we need to do as a RNS modular size, we should select the one of these. So these two options, 18 and 36, is unfortunately small for these parameters, and 72 is also larger than the word size. So what we did was we created kind of the virtual memory to utilize the leftover bits in the BRAM and URAM. And here is an example when we use 54-bit coefficient storage in a URAM. So let's say we want to store four coefficients in 4 different URAMs. And then in this case, we will have, as you can see, 18 leftover bits in each memory unit. Then these 18 bits will be basically wasted. But if we just create a virtual memory, and if we just use these bits, leftover bits, basically what we can do, we can just merge everything and combine them, and we can just reduce the URAM number from 4 to 3 to be able to, and we can still store the same number of bits in just 3 URAM instead of 4 URAM. And we apply this to our design for URAMs and for some of configurations of the BRAMs. And these provide us more than 20, in some cases 25%, and in some cases between 25 to 10% reduction in the BRAM and the URAM utilization. And then finally, again, to reduce the number of BRAMs and URAMs, we design the on-the-fly pivotal factor generator for the entity and inverse entity. So entity and inverse entity performs a transformation, and during the transformation, they require some constant called pivotal factors. And here is an example of how a single butterfly unit is working for entity, very high level. So we have one butterfly unit takes two coefficients and generate two coefficients. But during the computation, it also needs a third input, which is a constant. And one option is that we can store all constants of entity, required constants of entity and inverse entity in one memory. And the butterfly unit can read the corresponding constant for the butterfly operation and perform the butterfly operation and send data back to the memory. But of course, for large sizes, especially when we work with the homomorphic encryption, this constant memory will be really large. Specifically for an endpoint entity, during the entity or inverse entity operation, we need n different the constant for butterfly operations. And to be able to solve this problem, we just change the large constant memory with one small cache and a multiplication operation. So this cache keep the sum of the initial values here, and then what we do is we just read the data from cache, and we do the multiplication, and then the multiplication result are fed to the butterfly unit. If you want to give an example, for example, we have this. We will just keep the first three value here, constant 0, constant 1, and constant 2. Then read them by one and do the multiplication, and then we will be able to store. We will be able to generate the remaining ones without any problem. And this method, using this method, when we implement our entity and inverse entity, we were able to reduce the number of memory used for the pivotal factors more than 50%. And now I will talk about the placement-friendly layout that we propose for implementing our RPAW-based design into a multi-SLR FPGA. So as I said, for each RNA space, our design strategy was that using one RPAW unit and performing all the arithmetic units of this RNA space using one RPAW unit. But then when we look at the key switching operation, we see that the key switching operation requires some residual polynomials to be exchanged between RPAW units. For example, we have the RNA space 0 here, and we perform inverse entity. Then these results needs to be reduced by some other base, and then we have to perform again entity for the base. So in implementation setting, it means that after we perform this inverse entity in the RPAW 0, then we need to send this data to RPAW 1. And here we see the visualization of this. So we have during the key switching. So after we perform inverse entity, this needs to be distributed to all other RPAWs or all other threads. And this creates a huge problem when we try to map efficiently our RPAWs on FPGA platform, because now we have to place several RPAWs on an FPGA, and also we have to perform several interconnects between the RPAWs. So we experienced that this part of the design was extremely challenging. And one reason is that the structure of the Alveo board. So when we look at the Alveo board, we see that it is not a single chip, but it consists of 4 semi-separated SLR regions. As you can see here, it has 4 different the chips, and each SLR region is connected using a limited number of wires. So if you have a large design, just that needs to be consumed the 2 SLR region, then you have only limited wires in between 2 SLR regions to make the connections of one unit from here to the next SLR. And this makes things really complicated, because now if you want to place and interconnect RPAWs, now we have to consider these SLR to SLR connection constraints. And it took us like several months and the many different iterations to come up with an efficient placement and the interconnect strategy. Oh, and I will explain our solution with one example, where I assume that we use 10 RPAWs on a 4 SLR Alveo board. So the first and the naive approach is that we have, as you can see here, we have 10 RPAWs, and let's assume that each RPAW, each SLR region can only have enough resources to have only 3 RPAWs. And in this case, the first and the naive approach is that if you want to, because we need to send from one RPAW to all other RPAWs, then what we can do, we can have the common communication switch, where if you want to send data from RPAW 0 to RPAW 6, first data will be read from the RPAW 0, then will be sent to the RPAW 6. That's one option. Or we can have another direct communication from RPAW 0 to RPAW 6. That's also possible. But this approach is really complicated, because now we have to have many SLR crossing nets. And this complicates the placement and routing. And even for some design cases, tool was not able to finish the placement. And even if like it managed to do it, it achieves very low clock frequency. When we first design a straightforward design like this, what we was able to achieve was around only the 50 or less megahertz. Then after several iterations, we come up with this solution, what we call a ring interconnect. Now, to reduce the placement and the routing complexity, we limited the connection of one RPAW to only its neighboring RPAWs. And that way, now SLR to SLR crossing and the total routing on the FPGA is simplified. And now if you want to send a data from one RPAW to another, now it has to be performed through a chain of RPAWs. Let's say again, I want to send data from 0 to 6. Then what I need to do, because RPAW 0 can communicate only with the neighboring RPAWs, then first RPAW 0 has to send to 1, 2, 3, and from 3 to 4, 4 to 5, and 5 to 6. And that way, the SLRs crossing are minimized. The routing nets are also minimized, and we were able to achieve really high clock frequency, and we were able to achieve, for some cases, 250, and some cases 200 megahertz on our design. Then this part was the implementation aspects of our homomorphic processor. Now I will explain our design methodology to perform the flexible polynomial degree. So why do we need multiple polynomial degrees? Because based on the application and its complexity, it's possible that homomorphic application will require different parameter sets. So when we look at the parameters, we see two main things. The first one is the coefficient modulus, and the second one is the polynomial size. And the coefficient modulus, we already have this RNS structure, so it is relatively easy to achieve this flexibility. For example, if you want to increase your coefficient modulus, what you need to do in our setting, you just have to instantiate another RPOW. And that way, you can basically increase your coefficient modulus. Or similarly, you can remove some RPOWs to reduce the total number of coefficient modulus size. But for the polynomial degree, it's not that straightforward, and it requires some work. So how can we support the multiple homomorphic encryption parameter sets? So it's, again, if you consider software platforms, it is relatively simple, because most of the time what you need to do, you just need to change parameter, and for larger sizes, you just have to allocate more memory space. But unfortunately, it's not that trivial for the hardware implementations because of the limited on-chip memory, also the fixed wire of the components. Of course, you can try to make it reconfigurable, but this will increase the cost in some cases significantly. So then we try to come up with a solution for this problem. How can we support the multiple polynomial degrees in hardware? And then we come up with the divide and conquer approach for the polynomial degree. So idea was that we will have a design optimized for a small parameter set. And the idea is that we want to use this to support large parameter set. For example, we have one FPGA design, which is the fixed which works only for the polynomial degrees equal to 2 to the power 14. And of course, our application can require different polynomial degrees. It could be 2 to the power 14, 2 to the power 15, based on the requirements of the applications. Then, using this divide and conquer approach, this application should be able to use our accelerator, which can only work for 2 to the power 14, to perform actual homomorphic encryption homomorphic encryption operations for the much larger parameter sets. And here is like a mathematical explanation of the methodology. So we have this reducible polynomial f of the polynomial ring R, and it is in the form x to the power 2n plus 1. And let this zeta be the 4nth root of unity. And then we can rewrite this factor this f as fp and fm, where the fp and fm are x to the power n minus zeta to the power n and x to the power n plus zeta to the power n respectively. And then we can actually map the operations in this ring with this f to the smaller ones in these two small rings, which works with the degree n instead of 2n. So we take operation in this in this ring where the polynomials has the size of 2n, and we divide it into two smaller operations where the operations size is just n. And using this approach, we can actually perform we can actually use one design which is optimized for polynomial size n, and we can use it to perform operations for the polynomial size 2n. And of course, here we show how to perform this conversion between the 2n to n and the vice versa. And if you want to split a large polynomial of 2n, of size 2 and into the smaller ones. And this is how we can do it. This is our like the polynomial in the large ring. And what we need to do is we just have to perform this modular reduction with this smaller polynomials, which can be implemented in this way. Here the A underscore L and underscore H means that the lower part of this polynomial and the higher part of this polynomial. And when you look at this operation, this is actually can be easily implemented using the Cooley-Tukey configuration of entity butterfly unit. And now when we look at the join operation, where we take the two smaller polynomials and we merge them into one large 2n size polynomials. And in this case, what we need to do, we just take these two small polynomials, we just add them, and we just then divide them by 2, and then we subtract them, and we divide them by 2, and then multiply it with the modular inverse of zeta of power n. And as you can see, this operation also can be easily implemented using the gentleman's Andy configuration of a unified entity core. So as I said, if we have homomorphic operations with the polynomial degree 2n, we can easily now perform them using a design specifically designed for the degree n. And this is an example. We have homomorphic encryption for the large ring, and you just split them into two parts. And now you can use our architecture and you can perform operations and read your data back. And since as I showed, split and join part can be easily implemented using existing entity configurations, this operation doesn't require any extra hardware cost. And now I will present the evaluation results on an actual hardware. So what we present was mostly like design strategies. So you can apply these strategies to different parameters. So as a proof of concept, and our implementation uses 10 RPow units, and it supports two parameter sets. Of course, this 10 RPow is selected based on the limitation of our target platform. And the set 1 is working with the polynomial degree 2 to the power 14, and set 2 is working with 2 to the power 50. And here the resource utilization on Alveo board, and our processor in total is using 1.1 million LUTs, 800,000 registers, and 1.5 thousand VRAMs, and almost 1,000 URAMs, and 3.6 thousand DSP units. And if you look at the usage percentage, we see that we use the 72% of all URAMs and almost 60% of all VRAMs in our processor. And 10% of almost 10% of the LUT and the registers are spent on the platform module, which is responsible for the communication between our crypto processor and the host CPU. And this is the actual placement of our Medha architecture on an Alveo board. As I said before, because of the limitations of each SLR region, so we were able to place only 3 RPow units to each SLR. And again, we followed this ring-based interconnect strategy, and data transfer is happening again through a chain of RPow units. And here is the performance of the several homomorphic operations on an actual Alveo board. And what we did was we use actual hardware counters to measure the cost of each homomorphic operations, homomorphic addition, multiplication with the relinearization, and rescaling for 2 different sets. And for the multiplication operation, for the set 1, which uses degree to the power 14, latency was around 0.5 milliseconds, and for the set 2, it was around 1.3 milliseconds. And besides this micro benchmarking, so we show that we can use our architecture also for end-to-end application benchmarking. And for that, we use the logistic regression model proposed by the I-2017 competition winner. And we take this algorithm, we first implement it in the Microsoft Seal using our same parameter sets. And then we microcoded our hardware architecture. And then we compare 2 results. And the results show that compared to the Seal, our implementation of this, the logistic regression show 64 times speed up compared to the same implementation in the Microsoft Seal library. Now, I will present the comparison with the related the hardware and software works in the literature. And here I compare with the Seal and HEAX. At the time of our redesign and the submit our paper, the HEAX was the state-of-the-art FPGA-based homomorphic encryption accelerator. And when we compare our work with the HEAX, we show 2.3 times speed up to for different operations. And for the Seal, we use 2 different versions. First, we compare our work with the Seal, where we run on a CPU with the 2.3 gigahertz clock frequency. And also in the HEAX paper, they also present some results from the Seal, but to compare to their results, our Medha shows the much better improvement, around 134 times speed up compared to the homomorphic multiplication operation. And here we compare our work with the hardware-based accelerators, and we divide them into some categories, and we report several different results from each paper. The first category, as I said, as I mentioned at the beginning, is the ASIC works, were only focused on the simulation, the based results. So we have F1, BTS, Basilisk, Crater Lake, and Artwork, and they present really impressive speed ups with respect to the software. And however, as I said, they are consuming a lot of the area in the ASIC, and none of them are actually fabricated on actual silicon and tested. These results are obtained using C-level or RTL level simulation tools. There is only one ASIC work, CoFHEE, and it is actually implemented in an ASIC platform, but it only shows 2.5 times speed up compared to the Microsoft Seal. Then we have some FPGA-based works, which actually implemented and tested on real FPGAs. And compared to this HPP and the HEAWS, our Medha shows the much better performance. When we look at the numbers reported in HEAX, we see that they report the better speed up with respect to software compared to our work. But the thing is, they report a throughput-based the calculations. So they are a throughput-based, throughput-oriented design. But when we look at the latency, as I showed in the previous figure, we provide 2.3 times speed up compared to HEAX. And again, also finally, we present, we throw a speed up versus the cost graph. And here, as you can see, we have some ASIC works, and they provide really huge speed ups compared to the software. However, their estimated cost is around $10 million US. On the other hand, we have seen some FPGA-based works, and from ASIC side, we have is CoFHE, and they show relatively good speed ups with the reasonable costs. And here you see our Medha architecture. It's showing a good speed up with the really reasonable cost. And this concludes our paper. And very briefly, I will talk about the future scope. So there is one, of course, limitation of Medha we realize, and it's that this RPAW-based design is really good because now you can actually optimize each RPAW for a single parameter, and it gives you a really good room for the several arithmetic level optimizations. However, there is a drawback. So this leads to a low RPAW utilization when your multiplicative depth is low. Let's say you started with multiplicative depth 10, then you have 10 RPAW. In this case, during the first multiplication, you will use all RPAWs. But for the second multiplication, now since after one multiplication, one RNS modulus is dropped, then you will not be able to use one RPAW unit. And if you keep doing the multiplications, at some point the most of the RPAWs will be idle. Of course, this can be solved by turning these RPAWs into some reconfigurable RPAW units where they can support the more than one parameters. And as a feature scope of the Medha work, we target increasing the flexibility of the architecture by integrating support for the several homomorphic encryption schemes. Also, we will try to find the memory-based optimizations and the communication-based optimizations to enable the bootstrapping operation on FPGA platform. Okay, yeah, that's it. Thank you for your time. If you have any question, Mert and Aikata, we can answer your questions. Thank you.
Thank you guys for the presentation. I don't know if you have any question. Any question from someone in the audience? If not, in any case, I'll post the resources from your talk if it's fine with you, Ahmet and Aikata, on the FHE.org website.
Yes, sure, yeah.
And then people might have a question on Discord. So I love the recording. Maybe you can just send me your slide so I can add it to the recording.
Sure, yeah.
We have a question from Duke on the chat.
Okay. Is our design, the question is that, is your Medha FPGA design is the state of the art now? Actually, at the time it was accepted, it was the state of the art for the given parameter. But now there is a new paper, FAB, if you can check it. I think, if I'm not wrong, it presents a better results than our current work. Aikata, if I'm
Yes,
can you
Fab.
Yeah, you can. Yeah, Fab.
And also implements bootstrapping.